This is Mr. Martin. These are the video notes for section 5.4 for pre-calculus honors. This is day 2 of the notes. So we're going to look at 4 examples today, and as always, if you have questions, take the time to pause the video and write your question down, and then when you see me the next time, make sure that you ask me. It's an important process for learning the material. So for the first example, we want to write sine of tan inverse 1 plus cosine inverse x as an algebraic expression. So really what we're looking at here is we're looking at the sine of alpha plus beta, because this is some angle that has a tangent of 1, and this is some angle that has a cosine of x. So if we take a look at the two triangles that those would be part of, for alpha, we know the tangent is 1, so the opposite and the adjacent are going to be 1. So we know that the hypotenuse is going to be root 2. And then for the other triangle, here's my beta, and I know the cosine is x, so if I let this side be x and the hypotenuse be 1, then my cosine would be x over 1, or just x. And then I can solve for this third side. We'll call it b. I would have x squared plus b squared is equal to 1 squared. So b squared is equal to 1 minus x squared. And then b is the square root of 1 minus x squared. So that's what this side here is, the square root of 1 minus x squared. Okay, so now that we have our two triangles, I'm going to use my sum formula for sine. We've got sine alpha, sine beta, plus, oop, that's not right, let's fix that. We had a little trouble with the recording, I'm sure you noticed that. So sine alpha plus cosine beta plus cosine alpha sine beta. And I'm going to go to my alpha angle, triangle with alpha is the angle, so we want the sine. So sine is opposite over adjacent, so that's 1 over root 2. And for the cosine of beta, I'm coming down here. Cosine is x over 1 plus cosine alpha is also 1 over root 2. And then my sine of beta down here is square root of 1 minus x squared over 1. So I've got x over root 2 plus the square root of 1 minus x squared over root 2. And then if I rationalize this, I'm just going to multiply through by root 2 over root 2. I get root 2, x root 2 over 2 plus root 2 times the square root of 1 minus x squared over 2. And one final step, I get x root 2 plus, I'm going to combine these together, the square root of 2 minus 2x squared over 2. So kind of a messy answer, but that's what it does turn out to be. Moving on to the next example, we want to find the exact value of cosine 70 cosine 20 minus sine 70 sine 20. So if I rewrite this as cosine alpha cosine beta minus sine alpha sine beta, we can see that this is really the expansion of cosine of alpha plus beta. And in this particular example, alpha would be 70 degrees and beta would be 20 degrees. So if I substitute those in, I've got the cosine of 70 degrees plus 20 degrees, which is the cosine of 90 degrees, which is pi over 2, cosine pi over 2, which is 0. That's the x-coordinate up at the top on the unit circle. Alright, so there's our final answer. Moving on to number 3, find the exact value of the following function. So we want to find the tangent of alpha minus beta, and we're given a bunch of information here. This tells us that we're in quadrant 1 for alpha, and this tells us that we are in quadrant 4 for beta. So I'm going to look at my two triangles. My first triangle in quadrant 1, here's alpha. I know the sine is 3/5, so the cosine is going to be 4/5. And then my other triangle in the fourth quadrant, here's beta, and I know the cosine is 2√5, and this is 5. So we can use the Pythagorean theorem. I'm just going to save a little time, but if you calculate this, it comes out to -√5. If you have a question about that, again, make sure you ask me. Alright, so we've got tangent of alpha minus beta. That's going to be tan alpha minus tan beta over 1 minus, or 1 plus, tan alpha tan beta. Alright, so then we're going to refer to our two triangles to find all of these trig functions here. So tan alpha is going to be 3/4 minus tan beta is going to be -√5 over 2√5, -√5 over 2√5, and then it's going to be all over 1 plus tan alpha, which we figured out was 3/4, and tan beta, which we figured out was -√5 over 2√5. So a little bit of simplifying here. These root 5s are going to cancel, so that's just going to be -1/2 and -1/2 down there. So I've got 3/4 plus 1/2 over 1 plus, so that's 3/4 times -1/2, so that's going to be -3/8. So this is 5/4, this is 5/8, and when we multiply by the reciprocal, so I've got 5/4 times 8/5, and we end up with 2. So a lot of work, gets a little messy, ends up just being 2, so that's kind of a nice answer. Moving on to our fourth example, we want to find all solutions of this equation. So let's use our sum formula and our difference formula for sine and simplify these a little bit. So this first part here is going to be sine x cosine pi over 2 plus cosine x sine pi over 2. So that takes care of that. Plus, now let's use our difference formula for this. I've got sine x cosine 3 pi over 2 minus cosine x sine 3 pi over 2. So I know the cosine of pi over 2 is 0, so I have sine x times 0 plus cosine x times 1 plus sine x times cosine of 3 pi over 2, that's the bottom of the unit circle, so that's 0, minus cosine x sine of 3 pi over 2 is -1. So this goes away, this goes away, this is going to change to a positive, so I end up with cosine x plus cosine x, oh, and it's equal to 1, don't forget that, equal to 1, equal to 1, equal to 1, so 2 cosine x is equal to 1, which means that cosine x is equal to 1/2. So if we look at our unit circle, we know the cosine is 1/2 over at pi over 3, 5 pi over 3, So we end up with x is equal to pi over 3 plus 2 pi k, and x is equal to 5 pi over 3 plus 2 pi k. So nice problem because it combines stuff from section 5.3 and section 5.4. Again, if you have any questions, make sure that you write those down and you ask me. Otherwise, we will see you in the next video.